Yes.
Okay, so let's start the class. And I just want to go back to this slide here and to make something clear. Each time you have a resistance R, okay, so either it could be, for example, a resistor, so in that case it's just a R, or the resistance could be part of a load, like a light bulb, or if you have connecting wires, for example, you also have a resistance, right? So it means everything happens like a connecting wire also will behave like a resistance. Okay? So resistance here, that will be the symbol. And you see, let's say you have a voltage drop. So it's a voltage drop. So it's a property of 2 points. And let's say you have a current I going through it. As I've said, that equation here, the power, so it means how much energy is consumed by the resistance, is always equals to V times I. And that will be also true for a power supply. Is that clear? But when you have a resistance, you have alternative equation. Okay, so if you play V times I, and you know that V equals Ri, which is Ohm's law. Okay, so playing with those two equations, you see that the power, okay, so it means the energy consumed by the resistance every second is equals to Ri squared. Okay, or you can say V squared over R. So those three equations will be true for resistance. And so P equals V times I. It's true for power supply, for anything. Those two equations here, it's only true for resistance. Okay, we talked about that last time. Is that clear? Okay, good. So what's a resistance? A resistance will turn electrical energy into heat. Okay, so it's getting very, very hot, okay, depending on the resistance and depending on the current. So the amount of energy turned into heat will be equals to Ri squared, R squared times I. So it depends on the current and the resistance. So sometimes it's a good thing, right? So if you are using a toaster, for example, or if you are using a portable heater, that's what you want. You want the resistance to turn the electrical energy into heat. Okay, so when that happens, we call that the joule heating. So it means that the electrical energy is turns into heat. So if you have, for example, light bulb, you see that electrical energy is going to be turned into heat and light. Okay, you want more light than heat, of course. But that's the idea. So to decrease, if you want to decrease the amount of heat, you have two ways to do it. You can decrease the resistance or you can decrease the current. And I will show you two situations. Now, the other thing you want to understand is that each time you have a connecting wire, okay, so for example, here I have a connecting wire. Do you see how the wire is very, very, very long? That's going to increase the resistance. And of course, it's going to increase the loss of energy. I'm going to lose more energy to heat. Okay, I'm losing energy because my wire is so long. Okay, so any connecting wire has its own resistance. So for example, here, if we go back to that example here, you want all that electrical energy to be transferred just to the heater because that's what you want heat. Unfortunately, because you have a connecting wire here, some of the energy will be lost through that wire into heat because the wire will behave like a resistance and turn some of the energy into heat, which you don't want because if there is too much heat, you can start a fire. Okay, so if you have a connecting wire, so let's go back to the slide here. If you have a connecting wire, the resistance is proportional to the length. Okay, so if you have a very long wire like this one, that means the resistance is going to be larger. That means you are losing more energy. Okay, and it's to heat, and then it's inversely proportional to the area. If you have a thicker wire, like this one, you see you can have very thick wire, so you decrease the resistance. If you have very thin wire, okay, because you decrease the area, you're going to increase the resistance. So if you know that you can have a very large current, okay, and there is nothing you can do with that, then you need a very thick wire, okay, because if the current you cannot change, okay, you see that if you don't want to have too much energy turned into heat, then you need to decrease the resistance, so you have to increase the thickness of your wire. Does that make sense? So for example, here a heater, okay, is basically a big resistance inside. So it's gonna consume a lot of current. There is nothing you can do about it, okay? It wants 10 amps to work well. So that's why you need a very thick wire here to decrease the resistance. If you have a thin wire, okay, that's bad. Because if you have a thin wire, the resistance is going to increase and you are losing more energy to heat along that wire. And that's when the wire can melt and you can start a fire. That's why those portable heater, you don't want to let them unattended, especially if you have a cat, you know, the wire snipper, the snip the wires. So you make sure you unplug them, right? If you have a pet or even a dog. So I just have a simulation to show you here the resistance of a wire. If you increase the length, you're gonna increase the resistance, yes? If you decrease the length, you decrease the resistance. So they are proportional to each other. What about the area? So if you increase the area, you're going to decrease the resistance because it means your highway, imagine it's a highway, then it will be easier for the charge to flow. If you decrease the area, then the resistance is going to decrease. Do you understand? In addition to that, you can change the material, of course. So if you have a rubber, of course, or dry skin has a very large resistance. So even if you touch like a 12-volt battery inside your car, you should be okay if you have very dry skin. Okay, it depends on the material that you use. Okay, so the best material to use for wires, for example, will be copper. You don't want to use silver because it will be too expensive. Is that clear? So why do you need to use very thick wire in that case? Again, because the amount of energy that will turn into heat here, you see, it's turned into heat here. That's because that wire has its own resistance. So the amount of energy here that you are losing to heat, P, equals R squared times I. So not only it's proportional to R, but to R squared. So for a given current, because you know this is a load, so it needs to satisfy its appetite, it needs I. And here you have 120 volt AC. So this you cannot change. So you want to change R. Okay, so you want to make sure that R is as small as possible. So that's why you want to use a thick wire. You don't want to go to the dollar store and buy a cheap, very thin one because it can catch fire. Do you understand? So even in the chemistry, maybe you learn about that. It's called the Joule heating effect. Okay, it's when energy is turned into heat or thermal energy. Okay, so that's why you see those wires here. They are classified in gauge. So smaller the gauge, thicker is the wire. And you see that the very thick wire, they can take up to 125 amps. The very thin wire, it's going to be smaller than that. So that you have to be very careful with. Is that clear? So here you cannot change, again, the current you cannot change because that's what the load needs, but you can change the resistance to limit. So you want to make sure that the resistance is not too large. So you want to decrease the resistance, so you decrease that loss of energy to heat. Okay? Are you with me? Let's take another example. For example, here, you see, you have a power plant where electricity is produced, and this electricity here, the current is transferred to your house. So here you have 12,000 volt, and then at your house you have 240 volt. Now those connecting wire, okay, they have resistance, and you don't want to lose the energy because each connecting wire is going to turn some of the energy to heat. So they lose money. Okay, so the electrical company is going to lose money if they lose energy to heat. So they want to minimize that. Okay, so each connecting wire here will have its own resistance R, and the energy lost to heat is also equals to R squared I. And you don't want to increase those wire thickness because they are made of copper and it will cost too much money. So you don't want to decrease here the R. You cannot decrease R because otherwise that means you have to, you cannot make the wire shorter, okay? Because that's what it is, the distance between the power plant and your house. You cannot make them thicker because copper, especially today, is expensive. So the only way you have is to decrease the current. Do you agree? So here the power supply, it's going to provide you with a power V times I, okay? That will be how much energy is produced, and that amount of energy has to be transferred to your house. So let me ask you something. There is so much power you're going to provide, so that you cannot change. So this is constant, okay? You want to decrease the current flowing here because you want to decrease that loss of energy because of heat. What can you do? If you decrease I and you want to have P the same, what can you do here? You have to, very good, you have to increase the voltage. So that's why we have high voltage transmission line here. Those lines here, you know very well on your mother knee that you are not supposed to touch those wires, right? Because they are at 400,000 kilovolt. This is to minimize I, to minimize the loss due to heating. And then when you get to close to your house, you're going to bring down that voltage to 240 volt, and then you can use it. Okay? So the point is that any connecting wire will have its own resistance, and the energy lost, okay, to heat will be given by this equation here. So each time you have a resistance and you are asked to find the power, you can either use this equation, or that equation, depending on what is given to you. Okay? Is that clear? I had a demo, but I forgot my demo, so sorry. So no demo. Let's see. We stop in here, circuit in series. So let's do a simulation first. Let's see here. I have a circuit, so focus on that circuit here. It's a circuit in series because I have two loads, right? Next to each other. Is the current the same everywhere? It's like a pipe flowing. Is there anywhere for the current to go? Is it going to be everywhere the same? Let's see. Is it everywhere the same? Yes, right? You see, they are all moving at the same rate. If you imagine this is coulombs, right? So every second you have that many coulombs of charge being produced. That will be your amps. And it's everywhere the same, of course. Like imagine like you have a pipe, right? Water has nowhere to go, so it will be the same everywhere. So in a circuit in series, the current will be the same everywhere. Do you agree? As you increase the number of loads, of course, you're going to decrease the current even more. So for example, here I have, do you remember the current I had? What's the current? 0.75 joules per second. So 0.75 coulombs going through every second. Now, as I'm going to increase the number of load, I can put this one as a load. You see, now it's going to be even less. I have only 0.6. Okay, so as you add loads in series, you're going to decrease the current. Not only you're going to decrease the current, but you're going to decrease the voltage across the load, right? So we discussed that last time, I think. So let's look at the voltage drop. So across the battery, I'm going to have 30 volt. Across the 15, do you remember? It's going to be 11.25, yes? So less resistance, that means less voltage drop. So it's very unhappy, okay, because it doesn't get the 30 volt it deserves. And then across the 25, here you have 18.75. So then you add 18.75 plus your 11, you're going to get 30 volt. Is that clear? Kind of makes sense. We talked about voltage drop. Now, if I want to find the current flowing through that circuit, the mathematical trick is that you take a resistor here, one single one, and what do you think I'm going to do? You can replace that 10 ohm by 40. Very good. Exactly by 40. Okay. So if I put a 40 ohms resistance here, we did that last time. And of course, you want to read your book. 40 ohms. Let's see. You're going to find the same current. So any series of load can be replaced by a single one. Okay. With equivalent resistance equals to the sum of each individual one. Okay, is that clear? Now the voltage, of course, is going to be 30 volt. Is that clear? So it's not hard to understand. So now if I think we did that last time. So just a review. So make sure you read your textbook, of course. So if I add another load here, okay, it has a resistance 10. Okay, so that's how much it's gonna turn that electrical energy into heat and light. And you see that the current here has decreased even more. Okay, 0.6 volt. And the voltage, no one is happy now. Okay, no one get the 30 volt. This one gets 6 volt. This one get a little bit more, much more, because it has more resistance, so that's 15 volt. So 6 and 15, and here you have 9. So 6 and 15 and 9, you're going to get to 30 volt. Is that clear? So if I want to have the same current here, I need to replace the three of them by a resistance of 50. Very good. Okay, 50, and I'm going to get about the same current. Okay, sometimes I don't get exactly the same because sometimes you have like loss, you add some resistance because of the connecting wires. Okay, is that clear? So we did that last time. I had a nice demo, but I will upload the video of the demo in my YouTube channel. Okay, so we don't have to do it here. It's I did already a video. I will upload it. So if you want to check my YouTube channel. Okay, so what does it say here? I don't know, what does it say? Oh, I'm measuring the current, the voltage. Okay. Okay, so that's called a circuit in series. So let's take an example. Let's try to solve this one. Did we do that one? No? Okay, so we want to find the current. Let's answer the question. So you can talk to each other, try to help each other out. Someone sent me a flyer for a health care opportunity. It seems nice, but I don't know. Okay, I don't know them. They just I think it's a FIU student who sent me this, but you have to check. Okay, I don't know how good it is. Okay, don't blame me if it's not good. It looks nice, but you never know. I'm very suspicious of everything now. So I'll show you one way to solve those problems here. So first of all, you start with the power supply. Okay, so you start here, you follow the current to do. Oops, 6 ohm. So you're gonna make a 6 ohm there, and then keep going, keep going. Oh, a 3 ohm. So I'm gonna make a 3 ohm here, and you go back to base. Okay, I call that my ground. Okay, I call that the ground. Okay. So we can replace, so that will be a mathematical trick. We can replace these two resistors by a single one equals to 9. Okay, you just add them up. Okay, the way you can remember is you have a small zigzag here and you had another zigzag here, so it makes a big zigzag. So you have 6 zigzag plus 3 zigzag equals 9 zigzag. And imagine this is a pipe, so you have current flowing here. And then you can apply Ohm's law. Okay, so this is your ground. So this is ground, 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 ground. You start from 12, boom, you go to 0. So the voltage drop will be 12 volt. Okay, is that clear? So it's a mathematical trick to find the current provided by the power supply. So this is 12 volts. You put a times here and you use Ohm's law. So 12 equals 9 times I. Okay, so it's the voltage drop equals the resistance times the current flowing through it. And what do you get? 4/3 amps. Yes? Which is 1.33333. So then you go one step before, and now you know that will be the current, right? So the current will be 1 point, is that right? 1.33333, repeating amps. So the current here we know it will be 1.3333333, okay? And then you can find, what else do they want? Okay, A, the current. Okay, the power dissipated by each resistor. Okay, so that's easy because they don't even ask for the voltage. I will compute the voltage, but let's finish with the question. So we want to find the power, for example, dissipated by the 6 ohm. Okay, so power, so that energy will be turned into heat. Okay, it's getting very hot. And I have the resistance, I have the current. So I just have to do RI squared. Okay, and what do you get? 6 times 4/3 square. No, no, no. Yes or no? So you can do V times I. You can do that, or it's What's the power? Now I have like blank. Is it r square over I? No, r square I or ri square? No, I don't know. Ri square, right? And I say r square I before. Did I say r square I? Oh, yeah, ri square. Okay, ri square. But everything I told you is still true. It's the square should be on the I and not on the R. Or you can do V square over R. Okay. So that's gonna be how much is that? 10.666666, yes? Repeating? Okay. So Ri square and V square over R. And the power for the 3 ohms is gonna be what? Huh? Ohm. Okay? See, I did a mistake before because P equals V times I and V equals Ri. So P equals Ri square, not R square I. It's too bad I cannot rewind the class. Okay, sorry. So what will be the total power? So you do 10.66666 plus 5.333333. What do you get? Huh? 16 what? 16 watt. So that will be the power, the total power consumed by the loads, yes? Now can you find the power produced by the power supply? So this is consumed and I want produce. So V times I, right? By the power supply. So it's going to be 12 times the current, which is 4/3, which is 16 watt. So whatever is produced by the power supply, it's going to be consumed by the load. Okay? Sorry about that. I was so freezing in my office. I think it froze my brain. It was cold, so cold. I don't understand why it's so cold. Okay, any question? I hope I didn't confuse anyone. 10.6? Okay, so you find the power, and to find the power, you do Ri square. So it will be, okay, I will show you a different way to do it, but if you use the equation Ri square, which is now the right equation, it's going to be 6 times, and the current is 1.3333333 repeating, and that's how you find 10.6 watt. Yes? So each time you have a resistor, you have 3 ways to find the power. You can say it's Ri square, or you can say it's V square over R. So V, it's the voltage across the resistor, and I is the current going through you, not through you, through the resistance. Or you can say V times I. All those are equivalent to each other. Right? Is that clear? Yes. Yes. V square, how did I get that? Where does it come from? That's what you ask? So you can use that equation to begin with, And again, it's only an equation for resistance, right? So if you have P equals V times I, and from that equation here, you see that I equals V over R. So you substitute I by V over R. So V over R, and you get V squared over R. Okay? Conclusion. The power is always voltage times current, but if you have a resistance, you can use that equation instead. Ri squared or V squared over R. All these are the same. Okay, because you are using Ohm's law, V equals Ri. Is that clear? No? Let's check. Let's do it a different way. It's going to be the same answer. Let's do V squared over R. Let's see if we get the same answer. Can you compute the voltage drop here? Can you compute the voltage here? Drop. It's going to be what? It's going to be 8? No? It's going to be, let's find the voltage drop here, okay? So V across the 3 ohm equals 3 times 4 over 3, which is, what? Okay, 3.9, which is about 4. So the voltage drop here is 4 volts. Yes, do you all agree with that? So if it's 4 volts here, how much is it here? Across the 6. You want to add up to 12. 8. Okay? 8 plus 4 equals 12. Okay? Right? So let's find the power. So the voltage across the 6 ohm equals 8 volt. And you see it's twice as much here because the resistance is twice as much. So let's find the power. Power consumed by the 3. I'm going to use the equation V times I, and let's see if we got the same thing. What's the voltage drop? 4 times the current is 4 over 3. So we get 16 divided by 3, which is what? 3 goes into 16. Yes, 5.3 watts. So we get the same thing as before, right? Is that clear? You will get the same thing. And if you do the power consumed by the 6 ohm, that will be V times I. So it will be 8 times 4 divided by 3, which is 10.6 repeating watts. Okay? We're going to do more example. Okay. Let's do another example. Okay, why don't you try to do number, I don't know, number 1. Actually, number 1, you can do it in your head. So you have a 30 volt battery and you have 15 resistors of 10 ohm. So what's going to be the equivalent resistance? 150 ohms. Do you all agree with that? Okay, so can you find the current? So I can make the drawing. So you have 30 volt, and then you have a 10 ohm, 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 boom, 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 boom. So the equivalent resistance will be 15 plus 15, no, sorry, 10 plus 10 plus 10 plus 10 plus 10 plus 10 50 times. So that's going to be a 15 ohm. So far, so good? Okay, so what's going to be the current here? 1, 2, because the voltage drop here, you start from 30, boom, you go to 0. Okay, so the voltage drop is 30. Okay, so 30 equals 150 times I. So the current will be 30 divided by 150, which is 0.2. Is that right? Okay, so here it's going to be 0.2. What's going to be the power produced? Make sure you understand that. Produced, okay, by the power supply. It's going to be V times I for power supply. So it's going to be 30 times 0.2, right? Which is 6 watt. Do you agree with that? Let's see if I can use all my other equation. So let's see if I have power consumed by my 115 ohm. So I can say it's V times I, okay? But I can also say that it's going to be V squared over R. Let's check. What's going to be the voltage across my resistance here? 30 square divided by 150, question mark. So that's going to be, so 30 square divided by 150, you get 6 watt. And I want to check my other equation. Is it equals to Ri square? R is what? 150 times the current is 0.2 square. And that's going to be 6. Conclusion. When you have a resistance, the power consumed, you can write that down as V times I. So that will be the voltage drop times the current going through it. Or you can say is Ri square. Or you can say is V square over R. If you have a power supply, or if you have a LED or any kind of law that does not follow Ohm's law, then you just use this V times I. Okay? Is that better? Okay, so let's practice. Okay, let's do number 2. The best will be to help each other and talk to each other. Try to do it. You can draw if you want, or you can do it in your head, because it's easy. You have 3, you have a 20 here, and then you have a 20 here, and then you have a 20 here. So what's the equivalent resistance? 60. Do you all agree with that? It's like you have 20 zigzag plus 20 zigzag plus 20 zigzag, that will be 60 zigzag. Bless you. And you have current flowing here. Okay, so the voltage drop is 120. Okay, you go from 120, you go to base. So you have 120 equals 60 times the current. So the current will be 2 amps. Okay, I'm sorry, I don't know why I spaced out, but the current, the power is Ri square and not R square I. So maybe that's why I confused you. So what's going to be the power produced by the power supply? Hmm? The power produced by the power supply, how much is that? Yes, so V times I, it's gonna be 240 watts. Okay, So that means the power supply is producing 240 joule per second. Ask your gut. You have 3 loads. Each load, you see, it's the same thing. How much each one of them are gonna consume? So you have 240 cookies and you have 3 kids. So it's gonna be 240 and 3 kids. 80, right? So this one is gonna consume 80, 80, and 80. Do you understand? Okay, so it's like energy. You have 240 cookies. So this one is going to eat 80, this one 80, this one 80 because they have the same appetite. Is that clear? You can also, okay, let me ask you something else. Can you tell me what's going to be the voltage drop across each one? So you start with 120 and all the loads are the same, right? So they're going to have the same voltage drop. What's going to be the voltage drop? 40, very good. 40 volt, 40 volt, 40 volt. So I start with 120, boom, I'm going to fall 40, boom, I'm going to fall 40, boom, I get to 0. Okay? What else? You can even find the power consumed here by just this one. Okay, you can say it's going to be V times I. Let's verify. What's the voltage drop here is 40 times the current is 2. So that's going to be 80 watt. Or I can say RI square, which is 20 times, how much is I square? 4, which is 80 watt. Or I can say V squared over R, which is 40 squared divided by 20. You're going to get also 80 watt. Okay, does that clarify more about power? Right, I just, it's RI square, not R square I. Okay, any question? Okay, let's try our skill here. And I'm going to let you work this out. I want to know everything here. I want to know the equivalent resistance. I want to know the current and the voltage drop. Okay, so you can help each other and talk to each other, blah, blah, blah. So do it, okay? Don't stare. You have to do it. I'm going to use my other thing here. So they are in series, so you can, I'm going to make a drawing. So 90 volt. It doesn't matter which one comes first, okay? It's not like come first, serve first. So can you tell me what's the equivalent resistance here? 30? Do you all agree it's going to be 30? Ohm. So imagine it's like a pipe, so you have a current flowing here. You apply Ohm's law. So imagine it's a drop, right? So you have a voltage drop equals to, boom, 90. Do you agree? You start from a height of 90. This is base. So you drop by 90. So what's going to be the current? 3 amps. So that means the current flowing here is 3 amps. So you go back one step, okay, and you say, okay, so that means like it's one pipe here. So that's going to be, this is 3 amps. All the way, it's going to be 3 amps. All the way to base, it's going to be 3 amps. So all over, it's going to be 3 amps. Do you agree? Okay, so let's find the voltage drop now. Voltage drop, that means it's a property of 2 points. So I'm measuring the voltage between these 2 points. What's going to be the voltage drop? Very good, 30. You see, you start from the current times the resistance equals 30. Boom! How much is left now? 60. So between here and there, we're going to have 60. Do you agree? Okay, you drop by 30. So left relative to ground is going to be 60. But I'm going to measure the voltage here. How much is that? 3, 40. Very good, 45. Exactly. Tell me your name. I don't see. I'm totally blind from there. And how much is that here? 15. So can you see that 30 plus 45 plus 15 is 9 volts? Right? You see how it works? So once you understand that methodology is good, I just confuse you with this P equals Ri square. What's going to be the power delivered by the power supply? Huh? 90 V. What's the current being burnt out by the power supply? Huh? V times I, it's going to be 2, 270, 270 watt. Do you agree? So that power, V times I, it's going to be, some of it is going to be consumed by this one, some of it by that one, some of it by that one. Do you understand? So for example, the power consumed by the 10 ohm, I can say it's V times I. So how much is that? 90 watt. What? My God. 90, you know the joke, right? 90 watt? What? The power consumed by the 45. No, it's not 45, it's 15, sorry. 15, so it's gonna be 45 times 3. How much is that? 135 watt. What's your name? David? Steven. And the power, oh, I have another, I have 5 here. So how much is that? 15 times 3 is 45 watt. And everything goes well, you add everything up and you should get 270 watt. So this is called the conservation of energy. Okay, whatever energy is delivered, it's going to be consumed by the load. How much is consumed depends on the resistance. So the largest resistance will consume the most power. Okay, largest resistance means you can have more energy consume and turn that into heat. Okay? Yes. Will be this. So P, this one is the total amount of power produced by the power supply, consumed by all the loads. Now, usually in your book, they will do something like this, okay? They will say power supply is 90 volt, and then you have one resistance here, which is 10 ohm, and then another one, which is 15 ohm, and then another one, which is 5 ohms. And then they will say, okay, the current is flowing from this is plus, this is minus, so the current is flowing this way. Okay, and then you can have like a voltmeter. So this one you're gonna read here 30 volt. Here you have another voltmeter and you're gonna be 45 volt. And here you have another voltmeter and you're gonna see 15 volt. And you see that 15 plus 45 plus 30 equals 90. Okay, you with me? You don't space out? Now, let me ask you something. Do we have the same current here and there and there and there and there? Yes, very good. Okay, because there is nowhere to go. So I can open the circuit and I put my little ammeter here, multimeter, make sure it's to measure current, and that will read 3 amps. And it doesn't matter if I place it here or if I place it here or if I place it here. The current reading will be the same. Okay? Okay, so number 3, number 4. Christmas, yeah. It's another situation when you don't you don't want to have a cat, right? So 120 volt, and then um, you have 10 of them. So 1, 2, 3, blah, 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 10 of them. And so you can replace that with an equivalent resistance. What else is given? You know you have 10 of them. And replace that by one single resistance, and the current is 0.5 amps. So can we find the equivalent resistance? So 120 equals equivalent times 0.5. So equivalent will be 240, or yes. So 240 ohms, but you have 10 of them. So that means each one of them will be very good 24 ohm. That's going to be 24 ohm. That's going to be 24 ohm, and so forth and so on. Is that clear? Okay. Um, okay, a little bit challenging now. Number 5. Okay, think about it first. So you have only one to begin with, and it's a lamp. So what's going to be the current here? Very good, 1.5 amps. Do you all agree? And you are not happy with that? Now you have two ways to do it. You don't want to have the current that much, okay? This is too much. So what you want is to reduce the current to 0.5. So how can we reduce the current? We need to add a small resistance here next to my load of 10 ohm, okay, such as the current here is 0.5 amps. So we need to find another resistance. We need to add another resistance to reduce the current. So what's going to be the equivalent resistance here? If you have, is that 15? 15 and 0.5. Huh? Very good. 30 ohms, right? And you can see that here because if you want to have 0.5, if you want to divide the current by 3, the resistance has to be multiplied by 3. Or you can do that, okay? If you have a 15 volt here, what's going to be the current? No, if the current is 0.5, what's going to be the resistance? The resistance has to be 30 ohms. So if the total is 30 ohms and this is 10, how much is that R here? 20. So that will be the answer. Okay, so if you have a 20 ohms and a 10 ohms, everything happens like you have a 30 ohms. And 1.5 divided by 30 is 0.5. That's what you want. So you see, when you add the resistor, that's to decrease the amount of current flowing. Maybe there is too much current flowing, so you need to add the resistance. You multiply the resistance by 3, the current will be divided by 3 for the same voltage. Okay, so V equals Ri. So the same voltage, if the resistance is multiplied by 3, the current will be divided by 3. And this one stays the same. So if this one stays the same, if this one goes up by a factor of 3, this one will be divided by 3 or go down by a factor of 3. Okay? Okay. Uh, so the answer is, it's a one simple one. It's called a voltage divider. So you don't have to memorize it actually. Let's see how it goes. One more time. One more questions like that. So you have a 45 volt and you have a 5 ohm here and you have a 10 ohm. Is that right? 5 and 10. So what's going to be my equivalent resistance? Huh? Yes, 15 ohm. That's going to be the current. So the current will be 3. Is that 3? Okay, because the voltage drop, okay, there is only one load, so the voltage drop is 45 volt. So that now you go back one step. So that will be 3 amps. And what's going to be the voltage drop here? 15 volt. What's going to be the voltage drop here? 30. You see, 30 plus 15 equals 45. So you start from 45, boom, you drop 15, boom, you drop another 30. Okay? So it's a voltage. This is called the voltage divider because if you measure the voltage here, okay? So now I make a connection here. What's going to be the voltage drop here between here and the ground? It's going to be 30 volt. So it's going to be smaller than my 45. So in electronics, or if you play with Arduino, for example, you can use this schematic to have a voltage divider. So that means you get a voltage smaller than you start with. Okay, so if you measure the voltage at that point, it's going to be 30 volt. And there is a trick for that. I don't want to bother you with it, but you see the voltage here is V1 and the voltage here is V2. We can say the following: V1 or V2, okay, is to 45 watt, 10 is to 15. So that means the voltage drop here is to your power supply, what that resistance here is to the sum of the two resistance here. So that's called a voltage divider. You have the equation here. You don't have to worry about that. No, don't worry. Okay, it's just a parenthesis. So here you have the equation for a voltage divider. Don't worry. Let's skip that. Okay, any questions so far? Okay, so I want to talk about something called internal resistance. So inside any battery, okay, inside it, everything happens like you have a hidden resistance, like it's sneaky, it's inside, which means when you're gonna make your circuit, instead of having the 1.5 here, you're gonna have less voltage because some of the voltage is taken by that resistance here of 5. For example, here it will be 5 ohms. That's how a battery gets older. Okay, as you are using your battery, the resistance inside is going to increase and you are losing voltage here. So instead of having 1.5 volt, okay, you're going to have 1.5 volt minus that resistance here times the current. Okay, so it means there is a voltage drop, okay, inside the battery itself. So I want to show you, I have an app here, okay. Okay, so nothing special here. I have a 9-volt battery and inside there is no resistance that is hidden. So let's compute the current here is 1.2 amps. How much is the power supply? 12 volt. How much is 12 divided by 10? 1.2. So there is nothing surprising, right? It's a brand new battery. So if I disconnect the battery, okay, and I measure the voltage across the battery, it's going to say 12 volt. Okay, fine. And if I connect the battery again, it's going to say 12. Okay, so the writing here, it's called the EMF. Okay, it's what it says on your battery. It says 12 volt. At 12 volt, you're going to get. However, as the battery is going to get older, okay, there will be a small resistance hiding inside. So it's because of chemical reaction, but everything happens like inside here, you have a small resistance. And that small resistance is going to take away the 12 volt. It's going to eat a little bit, right? So instead of having 12 volts, you're going to have less. Let me show you. So it's getting old now. So I'm going to increase the resistance inside. Let's say it's 5. What's happening to the current now? It decreases, okay? Let's measure the voltage. Do I still have 12 volt? No, 8. I have 8. Why is that? Because you have 12 to begin with, 12 volt. Okay, how much is the resistance inside? We said 5. do 5 times 8, 5 times 0.8, 4. And how much is 12 minus 4? 8. Okay, so this is called the terminal voltage. So it means, like, let's split how much. Let's see how much you read. If there is no current, that's fine, you have 12 volt. But as soon as I make the connection, so the current is flowing, that little resistance here is taking away some of the voltage. Do you understand? So what's happening? Let's make sure you understand. So what was written on the battery? 12 volt. And then there is a sneaky little resistance inside, lurking in the dark. And it's a 5 ohm resistance here, right? So you cannot see it, it's inside the battery, and it increases with time. Okay, that's why if you have a battery, as they get older, they're gonna be hot in your hand because the resistance inside is increasing, so it's gonna turn more energy into heat. And then you have your load, and the load here is 10 ohm. And here you have 12. So what's the equivalent resistance now? So I have the lurky one, the sneaky one here, plus my load. How much is that together? It's going to be 15 ohms. So how much is the current? You do 12 divided by 15, it's going to be 0.8. Okay, so that little resistance here is stealing energy away, stealing voltage away. So you have here, you have 0.8 amps. So what's going to be the voltage drop now across the battery when it's connected? What's the voltage drop here? It's going to be 5 times 0.8. How much is that? 4 volt. How much is left for my load? 8 volt. Larger is the current, more steal there is from the sneaky little resistance inside the battery. Okay, happen the same thing with your car battery. As it gets older, there is a sneaky resistance here who keep that keep increasing, taking away the voltage that you need. So let's say you need 12 volt, all of a sudden you have only 11 volt left. Okay, so the 12 volt, it's called the EMF, but that voltage here will be 8 volt. That will be the terminal voltage. It's because inside the battery, everything happens like you have a small resistance hiding inside. Is that clear? That's why when the battery gets older, it's going to be very hot because all that energy is turned into heat, which you don't want. And then you lose voltage and you lose voltage and you lose voltage. And then at the end, it's useless, right? Instead of having 1.5 volt, you're going to have 1.3 volt, and then you have 1 volt, and then 0.5 volt, and you have to put it in the trash. Okay, so this is called internal resistance. So everything happens like inside your battery. Okay, you're gonna have internal resistance there hiding. Okay, so let's take an example. I don't know if it's a good example or not. I want to make sure it's a good example. Oh yes, because I work it out. Okay, let's do this one. Okay, that's good. That's a good one. If you have any question, I am available. Don't hesitate, okay? Um, so you have a car battery. You have a load that will be your headlight, for example, and the headlight has a, and I check online a headlight for a car. The resistance is about 30 ohm, and inside your battery, hiding, sneaky little resistance here is 1 ohm. I exaggerate, but let's say it's 1 ohm. And first of all, you need to find the current. So you have a power supply, 12 volt. This is what we call the EMF. And then you have one resistance here of 1 ohm. And then you have a load of 30 ohms. So can you find the current? So this is part of your, that's your battery here, right? 0.4, so the equivalent resistance is 31, so you do 12 divided by 31, 0.4, about 0.4. 0.4, about 0.4 amps. Yes? Okay. So what's going to be the voltage drop here? So it's going to be 0.4 times 1 is going to be 0.4 volt. So how much is left here? 11.6 volt. So it means when you are connecting the battery, when you start your car and you have your headlight on, instead of getting the 12 volt, you're going to get only 11.6. Okay, so this is called the terminal voltage. Terminal voltage. Is that clear? So because of that little resistance hiding inside, you lose some voltage, and instead of having 12 volts, you're going to get 11.6. You cannot see that. Like if you take a voltmeter and you measure the voltage across your car battery, you still see 12. It's only when you connect everything that you see that you don't get the 12, you get something less. Okay? Is that clear? So let's do, and that's from your Johnson and Cutnell book. Okay, you can see that here. Okay, I have a nice schematic that I have found. Inside the battery, okay, you have that little internal resistance. So you have the EMF like 12, and then you have a little resistance hiding here, which is 0.01. So the voltage available to the load is going to be less. Okay, so let's try to do this one. You can help each other. Don't, I see people spacing out. Don't space out. Stay with us. Don't space out. Okay, stay with us. Help each other. So you start with 12 volt. And then you have a sneaky little guy here. No one wants it, but it just came in. And then after that, you have a load. We don't know how much the resistance, but here you have a load. Okay? And it says first the current is 10 amps. So what's going to be the voltage drop here across that load here? That no, it's not a load, the internal resistance. What's going to be the voltage drop? 0.1. Very good. So how much is left for the load? 11.9. Okay, so your load does not get the 12 volt it was promised. It's getting less because there is a fifth inside. And that's because of chemical reaction. Like if you open your battery, you're not going to find a resistance. It's just everything happens like. And this is called the terminal voltage. What is left after the stealing? Can you do the next one? So 12 volt. Okay, and then you have this sneaky little guy here. Okay, and then here, this is your battery. And then here you have a load. And you go back to ground. And the current is 100 now. Okay, that's a typical current for a car battery. So what's going to be the voltage drop? 1 volt. Oh, yo. Terrible. So how much is left for your load? 11 volt. So this is what we call the terminal voltage. Now your battery, the battery is the whole thing here. You don't see here, it's a black box. Okay, so across here, instead of having a 12 volt, you're gonna get a 11 volt. Okay, that's because there is a voltage drop inside. Any question? Very good. So it will be the terminal voltage across your battery. So for example, if your car is running and you come with a voltmeter and you measure the voltage here across the plus and the minus, you're going to find 11 volt, regardless of whatever load you are using. The loads that you are using, maybe you are using two headlight and the radio and the GPS or whatever. Okay, you can have a lot of load here. But if the load are consuming needs 100 amps, okay, so because of that resistance here, you have only 11 volt available for the loads that you have connected to your battery. If you disconnect everything, then it's back to 12 volt. Because if there is no current, there is no voltage. Okay, so V, the voltage equals Ri. So if the current is 0, okay, the voltage equals 0. So if there is no current flowing, then there is no voltage drop. And you think that you are okay. And then you start your car, and the car is not starting, so you know there is a problem with your battery. Because you need a battery to start your car, okay? You need some voltage for your starter. Is that clear? Okay, so any question? So let's do, for example, this one. So you have 1.5 volt, okay? And there's a 5 ohm resistance lurking inside. And the current is 60 milliamps. How you convert that to amps? Divide by 1,000, right? So that's going to be 0.06, yes? 0.06 times 5, how much is that? 0.30. So 1.5 minus 0.30, how much is that? 1.2. So this is called the terminal voltage because some of the voltage has been stolen by the internal resistance. Okay, so this one is not happy. It was promised, in the contract. It says I need 1.5 volt, and here we go. It only gets 1.2 volt. That's when the battery is dying. Okay, that's what happens. Any question? Okay, so let's go back to here. So this is not a good circuit for house, like for the house. That will not be good because if you have a load with a high resistance, it's gonna take away all the voltage, right? So we never do this kind of setup. Instead, we're gonna have what it's called a series circuit, a circuit in parallel. That's the real Christmas thing. They have in series, you have in parallel. Okay, so let me show you. If I have now, and I had a demo, but forgot the demo. I'm gonna take light bulb. So these are loads. I'm gonna take 3 of them. I'm gonna take a battery here. 9 volt. Okay, fine. We can take it. And each one is 10. Okay. So 9. How much is the voltage across each of them? 3, right? So here you have only one. If I take only one here, if I connect, is it happy? Yeah, it's happy. Look, let's check. Does it get the 9 volt here? It was promised. Yes. Okay. And the current here, I can measure the current. It's gonna be 0.9, right? So 9 divided by 10. Okay. Now I'm gonna build a circuit in series, and they are not going to be very happy because I'm gonna take 3 of them, and now they have to share, and they don't like to share. Okay, can you predict the current? Yeah. So it's always the voltage divided by the resistance is going to be the voltage. Not necessarily 10. It depends on the resistance of the load. I can change the resistance here, and you see it's not going to be divided by 10. So here, if I change the resistance, you see the voltage is going to increase, and it gets even worse because if it has a very large resistance, it's going to take everything and nothing is left for the others. You see the unfairness? It's terrible. They are. Let's keep it this way. You see how unhappy they are? You see the current? How can you find the current? What is it that you do? You have a 9 volt. What's going to be the total resistance? 140. So if you do 9 divided by 140, you get 0.06, right? If you want to find the voltage, you will do 120 times 0.06, yes? Can you do that with your calculator? You do 0.06 times 120. Do you get 7.70 about? Yes? Okay, let's do this one. This one is crying. Can you hear it crying? Look at that. 0.64 volt. It was getting 9 volt, and now because the resistance is small and it has to share with this one, the voltage is only 0.6 volt. How do I do? I know that. I do 10 times 0.06. What do you get? 0. Exactly. So it's not happy, and this one is not happy either. It's got the same thing. Okay? So that will be very bad because in a house, if you have a microwave and then you have a lamp and then you have audio, one of them is not going to work. So we don't do that way. So the way to do it is what it's called a circuit in parallel. So each one, so this one is happy. And now I'm gonna add this one. Okay. He wants also to be connected to the battery. I don't know if it can get very messy. And then here, now is it happy now? You see, this is called in parallel because both of them, how much voltage do they get? 9. Okay, they get 9. This one get 9, so it's happy. Okay, because it's connected to the positive and the negative of the battery here. So now it's happy. And this one gets 9. Okay, and they can drain as much current as they want. And I can keep adding. I can put another one here if I want. And connect that here. And now it's happy. So this is a circuit in parallel. There's a price to pay. What do you think the price to pay is? So the voltage here is the same, but you are draining more what? Current, because you need to satisfy this one, and you need to satisfy that one, and you need to satisfy that one. So the current that you are draining from the battery is much, much more, 1.87. And how much do you drain here? 0.07. How much do you drain here? 0.9. How much do you drain here? 0.9. When you add all the current, you're going to get to this one. So that's what we have in a house. We connect all the loads in parallel. So each one get the same voltage, okay? And the current it needs. If it has a large resistance, it's not going to drain a lot of current. If it has a small resistance, it's going to drain a small resistance. So everything happens, it's plugged individually to the outlet. Okay, so that's the way you want to go. Okay, I think do you see